controlling the Sosis robot. So the robot Sosis is the robot, underwater robot represented in this picture. So the robot has 3 propellers. So we can see one propeller here. So we make it possible to change the altitude. We have one propeller here, which make it possible to exert forces like this, and another one on the right side of the robot. So here it's front. So this robot has 3 degrees of freedom, so x, y, and z, and it can move in all directions. So the speed can be longitudinal or lateral. This is why I may have a speed with respect to x, a speed with respect to y, and a speed with respect to z. So it means that the robot can move laterally like a crab. We assume that the robot is stable in roll and pitch due to the fact that you have more masses here. We can see here a sonar for localization, but we'll not care about it. We'll assume that all the state of the robot is known. So we'll not implement in this exercise some observer in order to estimate the state variable. We'll assume that they are known. So we are this robot is a very slow robot. So for low speed, we assume that the friction can be neglected. And in this situation, we may assume that the robot can be described by the following state equation. So the state will be the degrees of freedom x, y, z. I also have to add the heading psi, the speed, and also the rotational speed. Okay. So if I assume this as given in the exercise, we know that the derivative of x is equal to vx, the derivative of y is equal to vy, the derivative of z is equal to vz, the derivative of the heading psi is the rotational speed omega, and now I can control different speed. So for this one, due to the 2 propellers here, I can assume that I can control the acceleration with respect to this direction, but also laterally. So due to this, I may assume that Vx is equal to u1 cos psi and Vdox y is equal to u1 sine psi. So it means that if I draw here the robot from the top, like this, here it's front. I have 2 propellers, one here and one here. And u1 corresponds to the acceleration in this direction. So it corresponds to the sum of the speeds of the 2 propellers. Now I have also Vz is equal to the acceleration with respect to the z direction. So since here it's a propeller number 3, it is related to this propeller and I can control it directly. Since I have low speed, I do not take into account the friction. And also omega, the rotational speed, is equal to u2, and u2 corresponds to the difference of speed of the controller 1 and of the propeller 1 and the propeller 2. And the first question is to draw the differential dependency graph associated to this system. So we'll see later that the output will do a control with respect to x, y, and z. And the differential dependency graph will be used to compute the relative degrees. So here are my state equations. I remove this. I can see that I have several state variables that should be taken into account. So I have x, y, and z. So 3 state variables. I will have also as a state variable Vx, Vy. I will have also omega and Vz. And I have also 3 inputs, U1, U2, U3. Now, I will consider all the state equation. And I know there is so the dependency graph will tell me that, for instance, in this equation, Vx has an influence on x. So this is what I put an arrow like this. It means that there is an integral separating Vx and x. So it is this one. Now the other one is this one. I draw this arrow. Oh, I should have also another variable psi here, so I should put it here. So z dot equal Vx, I have to put this arrow. Psi dot equal omega, so I have to add this. Now about these two variables, it means that Vx, which is here, depends on u1. It is also the case for Vy, but also depend on psi. This is why I have this. And omega dot equal u2 and Vz dot equal u3. So it is the differential dependency graph of our underwater robot. So from this, we are able to draw the differential delay matrix. So it corresponds to the question number 2 of the problem. So we choose as an output y equal to x, y, and z, and we should draw the differential delays matrix and to deduce the relative degrees from it. And then we have to conclude. So I have this one. And the delay matrix. So each row corresponds to one delay. Here R is a 3-3 matrix, where here I have corresponds the first column to U1, this one to U2, and this one to U3. This line, I have also 3 lines. This line corresponds to the first output X, this one second output Y, and this one to Z. And I have now to compute the smallest path, the length of the smallest path, separating two pairs of variables. So for instance, if I take U1 and X, the shortest path is 1 plus 1 equal to 2. This way here I have 2. Between U1 and Y, 1, 2, 1, 2. So here it is also 2. Between U1 and Z, there is no path, so I should put a distance of plus infinity. Now, between U2 and X, so I have 1 plus, excuse me here, there is also an arrow, an arc here, between psi and Vx. Due to this, there is a cos psi. So 1 plus 1 plus 1 plus 1 is equal to 4. Between U2 and Y, 1, 1, 1, 4 also. Between U2 and C, plus infinity. Now, between U3 and X and Y, there is no path, so it's infinity, infinity. And here, 1 plus 1 is equal to 2. So the relative degrees corresponds to, I have to take the minimum to get the relative degree. It corresponds to the distance between x and one of the input. So here the shortest path corresponds to 1 plus 1. The minimum of this line is 2. Here the minimum k2 is equal to 2, and k3, the minimum of this line, is 2, excuse me. So I can observe that when I will differentiate x and y, u1 will first appear and u2 will appear if I derive 4 times. So it will be a problem because the A of x matrix of the feedback linearization method will be structurally singular. So it means that in the x and y derivation, u1 and u2, so the two inputs, should appear both together. So this is why I will have to delay u1 by adding two integrators. And if I do this, I will have a new input, let's say a1. This one will correspond to a2 and this one to a3. So they will not change. And if a is a new input due to this integrator, so this corresponds to the vector a, and this corresponds, and this corresponds to the output. So I will have after this an equilibrium, a balanced situation, because when I will differentiate x or y, a1 and a2 will appear both together. So question number 3. As we have just suggested, we have to balance the differential delay by delaying u1. And for this, we add two integrators in front of u1. So the new inputs will be named a1, a2, a3. And I will have this relation. And I now have to write the new state equation to draw the differential delay graph and also the differential delay matrix. So the differential delay matrix is represented on the picture, already depicted on the picture, where here I have A1, here it corresponds to B1, this one will correspond to C1 or U1, so it is also a state variable. So I prefer sometimes to call C1 because U1, U2, U3 will be the input, so sometimes I will make the confusion between C1 and U1. Okay, so from this I should add two state variables, one corresponding to B1, one corresponding to C1. This is why I should add here, due to the two integrator, C.1 equal B1 and B.1 equal to A1. So it means that what I have added here corresponds to the same that if I take this, where the input is U1, U2, U3, the classical input, and here I delay by adding two integrators. A1 is this, A2, A3, and the new state variable are stored inside the integrators corresponds to B1 and C1. Again, we see that C1 equal to U1. So if I add these two integrators, I will have new state equation like this. And the state equation are now described by all this, except probably that here I should change U1 by C1. C1, so I try not to use anymore U1, U2, U3. This one becomes A2, and these ones become A3. So in this case, I have a new state vector which is Z, corresponding to X, Y, Z, Vx, Vy, Vz as previously, but I have C1, C2 as B1 as this new state variable. So in this case, if I rewrite using a vector field notation, I can write the state equation like this. So x dot 1, y dot 1, z dot 1, vx dot 1, y, excuse me, I have forgotten, psi dot vx dot vy dot vz dot omega dot c1 dot and b1 dot. So this corresponds to z dot. So this is equal to, so here Vx, Vy, Vz, omega C1 cos psi, C1 sin psi, 0, 0, B1, 0. So here I should add also something like this, where I have only A1 plus something like this, A2, plus here A3. So here I have 1 and only zeros here. Here 0, 0, 1 after only zeros. 1, 2, 3, 1 and only zeros. Okay, so it is important to write like this if I want to use Lie derivatives with symbolic calculus. So this one corresponds to what I call f z of z. This one is g1. It should depend also on z, so g1, j2 and j3, but here in this particular situation they do not depend on z. And here it is the inputs. So normally fz, g1, g2, j3 corresponds to vector field since they correspond to an application which to z associate a vector which has exactly the same dimension as z. So b1 and c1 correspond to the state variable attached to our two integrators. Now I can write the delay matrix in this new system, and this, so in this situation this one will be now A1, A2, A3, and this will be the same except this one, it will be 4 and 4. Question number 4, I now have to propose a controller based on the feedback linearization method of the balanced system. So with the two integrator in front of it. So for this, the classical method is to take the output. So the outputs are x, y, and z, and I will have to differentiate them. This one 4 times because the relative degree of x is 4. K2 4 times also, and this one I will have to differentiate it twice only because K3 is equal to 2. So I can do it by hand. I will do it by hand now. So first I take x. So x is equal to the derivative of li with respect to z. So I differentiate 0 because at the moment I do have dots on the x, and I will differentiate the function x. And if I do this, I will obtain x. This one probably is too simple. It's only bring confusion. But now x dot. X dot is the derivative of li with respect to this vector field of x, which corresponds to Vx. So of course, this one I will use for symbolic calculus, all this column. But at the moment, it's only bring confusion. But if I want to use symbolic calculus, I will have to express in this way. Okay, now x dot dot is equal, I have to differentiate twice now of z with respect to x. And since x dot dot is corresponds to Vx dot, which is equal, so I take this line, this one, I see that it is this, so I will write here C1 cos psi. I will have also to compute this one, Lie derivative of the third order of x, which is equal to c dot 1 times cos psi plus c1 psi dot minus sin psi minus plus minus. Okay, and now I know that this one is c dot 1 is equal to b1, and psi dot 1 is equal to omega. Okay, this is why it corresponds to b1 cos psi minus c1 omega sin psi, and up to now there is no inputs, no a1, a2, a3. But now, since the relative degree is 4, it should appear if I write this 1, 2, 3, 4. So if I write this, I should write that it is, in this case, the expression is a little bit more complex, so it will be L Fz. I derive 4 times, but since I have the inputs, I also have to add the derivative of G1. Oh, this one is G1. 3 Fz of x1, or x1 is x, I should write x here, plus times u1, a1, it is a1 now, plus lj2 derivative 3 fz of x times a2 plus lj3 l3 fz of x multiplied by a3. Okay, so it is a little bit more complex, but if I write into a matrix form, I will do this for all x, x dot, and so on, I will obtain something like this. X, so for derivative, so I probably will write like this. X differentiate 4 times, y 4 times, z I derive twice, and this corresponds to a matrix. So if I compute all of this, and I will do not do it here, it is cos psi minus c1 sin psi 0, sin psi c1 cos psi 0 times n1 a2 a3, and 0 0 1 plus an expression which is something like 2b1 omega sin psi minus c1 omega 2 cos psi, 2b1 omega cos psi minus c1 omega square sin psi, and here 0. So this is an expression which is a of z, and now this one is b of z. Now if I don't want to compute all by hand, I should write directly that a of z is a matrix where the first component here is Lj1 Lfz derived twice of x, and here I will have the last one will be Lg3 Lfz of z. Here I will write also the last one, Lj3 Lfz of x, 3 here, also here, Lfz of y, derived twice. Okay, so I put here a 3 and here a 1 because it corresponds to k1 minus 1, here k2 minus 1, and here it will correspond to k3 minus 1. This is why you see here I have a 1 only. And the first one here, so I have 3 lines and 3 columns. So the first one here will be Lj1 because it is the first column, Lfz of z. So I take the SIMP library in Python. I replace the Lie derivative by the operator L here, and I perform a recursive implementation with where A is the number of times I want to differentiate. The matrix A that has previously been computed is computed in the program here. So I can recognize here that I have a Lie derivative respect to J1, and here it is the third Lie derivative of this one, which corresponds to x1 corresponds to x. So for this I had to create in Python using SIMP the coordinate system, because all fields will be in this space which correspond to the state space. So x1, x2, x3, which correspond to x, y, and z, the heading, the speeds, rotational speed, and the integrators c1 and b1. I create my coordinate function, so I need my field and I also need the coordinate functions. I create my main field f corresponding to the dynamics when the inputs are equal to 0. They are given here. And they are expressed with respect to the vector field of the main bases. So here J1, J2, J3 corresponds to also are built from the canonic, from the base vectors field. This one is a 9 because I recall that J1 has zeros everywhere except at the 9th position where you had a 1. And here it is the same, except that for J2 it's at the 7th position, and here the 6th position. So I have my A matrix, and I also have my B matrix, which is implemented here. So recall that, for instance, here I have this, because previously I had this, and this are inside, so correspond to the first line of the matrix A. So here, here, and here, where this one was corresponding to the first element of B. I switch to Python, I run the program, and I see here my matrices that corresponds to A here, and B here. I can obtain exactly the same using by hand. The computation is not so difficult, but for more general system, it's much more comfortable to use symbolic calculus. So I have this expression where here are the derivative up to the relative degree of the three outputs, and here it corresponds to x, y, and z. Here I could have computed these matrices by hand, but I will try to do everything using symbolic computation. What I want is that this derivative equal to exactly what I want. And exactly what I want means another input, v1, v2, v3. I can choose these values as I want, so I will choose A equal A minus of z, to cancel this one, minus v, this vector, minus b of z, this vector. So if I choose this, then I will have this equal to this. So it means that the loop system with this control law will be equivalent to the system with 4 integrators here, so 4 due to the relative degree, v1 x, 4 integrators where I have y here and v2 here, and 2 integrators where here I have z. So this is, with this control, my robot plus this control is equivalent to this decoupled linear system. Okay, so to be more precise, this is my original system. This system had 3 inputs, U1, U2, U3. I have to add two integrators here, where here it is B1 and C1, what is stored inside the integrators. Here I added a system which corresponds to A equal A minus 1 of Z multiplied by V minus B of Z. The input for this one corresponds to X, but also B1 and also C1. So it corresponds to the vector Z. I have for this system an input V, and this will produce two outputs, A1, A2, A3. A3 corresponds to U3, A2 to U2, and this one goes to the first integrator. This whole system here and this system are equivalent. So the output here is X, Y, and Z. They are both equivalent. So now I will find a method to control this first system, and I will apply to the other one. Okay, so for this I will apply a proportional and derivative control for this one, and I will write V1 equal, so the error will be, what I want is omega 1 minus X, so omega 1 is the input I want for X. So this corresponds to the error E1 plus omega dot 1 minus X dot 1 plus the coefficient, of course. Here I will write also, it corresponds to E1 dot, so the derivative of the error, omega dot dot 1 minus LFZ, excuse me, X dot dot 1 plus W dot 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 1 minus X1 dot dot dot, and plus omega dot 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 dot. Okay, so since I do this, and since this one corresponds to X1 dot 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 dot, then the error, the differential, the error will satisfy. This one corresponds to X dot dot 1, and here E dot 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 1. And due to this, I will have a differential error, an error differential equation for the error that may converge to 0 if I choose the right coefficient. So for instance, here I would choose 4, 6, 4, and 1. So the characteristic polynomial corresponds to S plus 1 cube, and then it means that it will converge to 0. Indeed, in this case, the error will satisfy the differential equation E1 plus 4 E dot 1 plus 6 E dot dot 1 plus 4 E dot 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 1 plus E 4 times. Okay. This is equal to 0, and 0 will converge to 0. So I can do the same for V1, the same for V2, and for V3. what we can see here is this. I know an expression for w of t. It can be a polynomial, for instance, but I know an analytical expression, so I have no problem to have the derivative. Now, for these quantities, I can have a derivative, an expression of the derivative, since I know the expression of the state with respect to itself. So this one corresponds to the Lie derivative of z of x1. This one, the Lie derivative of x1, and here's the third Lie derivative of x1. The expression of the proportional and derivative controller is given here with respect to the Lie derivatives. The input is v. The input are the w of t, which is given under the form of a polynomial, for instance. And I will the output and also the state z, and the output will be the v. I will write this expression under the form v equal a function phi, which depends on w of t and their derivative, and z. So if I come back here, I will have the v here. I will write v equal phi of w of t and z. It will generate v as an output. The input will be w of t. Z is needed here, like here. And the whole controller of this system is given here. This is the controller. I will call it, let's say, rho. Here it is x. And inside this controller, we have two integrators that corresponds to the memory of my controller. Okay, so now we'll have to check the singularities about a of z before the simulation. It is important to recall that the trajectory, the wanted trajectory w of t, has to be differentiated 4 times to build the expression for phi. The global approach is called a dynamic feedback linearization. Dynamic, why? Because there is a memory inside the controller. Here it is the expression of my program, which will build the regulator. So I still have my coordinate system. I build fz here. My field j1, j2, j3. This corresponds to v equal phi of w of t and z. And we can understand that they are linked to the Lie derivative to get here the derivative of the error. This one is a classical differentiation with respect to t because I have an analytical expression. Indeed, in my program, I have taken this expression, which corresponds to a Lissajous curve, a three-dimensional Lissajous curve. And if I switch to Python, I run the program and I can see the expression for my function, for my regulator, which is quite heavy, and it is much more comfortable, even for this simple system, to use a symbolic calculus. Question number 5. I have to provide a simulation of the controlled robot in the case where the wanted trajectory is a Lissajous curve, which the expression of which is given here. So normally, if everything is correct, I should obtain here the reference point. At the beginning, after some initialization, the robot will converge to the reference point exponentially. And at the end, I can see a view from the top and a view from the side. And we can see that I have some kind of ellipse if I look from the bottom. And here the robot goes up and down. Okay, so now for the simulation, I propose first to simulate the system without the controller. So this one corresponds to the evolution function because my system, my robot satisfies this expression. So here it's f of x and u. And I can recognize the evolution function f here. Here is just to paint the robot. So for this I use 3D axes with some Euler matrices just to draw, and the reference point is named here W1, 2 and 3. For the integration I use here an Euler formula, and here I ask to paint the robot as the state x, but also the reference point w of t, which is given here. Okay, the star here is to unpack the result because it will be a list of 3 elements, so I have to unpack so that here this one will be transformed into w1, w2, w3 as asked by the function draw. If I take this program, I run it, I can see here my robot moving without any inputs. So, and this one is a reference point. I propose the following program for the simulation. I have here my reference trajectory w of t, which corresponds to this. Here I build my regulator with the A matrix, the B matrix, and this corresponds to phi. So this one corresponds to phi of w of t and z. So z corresponds to all these variables you have inside x, but you also have c1 and b1 corresponding to the 2 integrators here and here. Okay, the symbolic part makes me possible to change very quickly the W or the state of the system, which is quite comfortable when we change a model during the conception step. Here I build my regulator and I lambdify in order to transform my expression into a function that can be called by Python. Here it is my initial state vector, so only for x, and this one is for the 2 integrator c1 and b1. Here it is my main loop for the simulation. I call here A, so A here, A1, A2, A3 are built here using the function rho that first been computed with SIMP. Then I will build U as explained here, taking C1, A2, A3. So C1 is the output of the second integrator. Here it is an Euler formula for the evolution of my robot. Here it is an Euler formula for the integration of the 2 integrators, so the memory of my regulator. I run the program. I can see that the AUV reach the target point. In red, I represent the longitudinal and the vertical propulsion. And we can see that it follows exactly the reference point. The orientation we have for the robot is mainly due to the fact that the propulsion is only allowed with respect to the axis of the robot. This is why it has to orientate toward the origin so that it will be able to turn around it following the Lissajous curve.